Hello, aspirants. So, in the spectroscopy principles, we have seen UV visible as well as infrared spectroscopies in the previous two modules. And in this module, or the last of the spectroscopy module, we are going to see atomic absorption spectrometry. Let us see more details about atomic absorption spectrometry or AAS in the coming slides. Atomic absorption spectrometry AIS is a technique for measuring the concentration of metallic elements in different materials. So basically the application of this AIS, atomic absorption spectrometry, is confined to elemental impurity analysis or elements analysis. Metallic elements generally analyzed through this particular method. As an analytic technique, it uses electromagnetic wavelengths similar to the IR coming from a light source. Distinct element will absorb these wavelengths differently. That is the basic principle behind this particular AAS technique. So each element absorb this light in different wavelength. And when the light is absorbed by these elements, the atoms of the elements will have their own characteristics, and the element has a unique electronic structure. As atomic absorption spectrometry also follows the Beer-Lambert law, so it measures a specific element in a material based on the amount of light absorbed at a defined wavelength, which corresponds to the known characteristics of the element which is under testing. So the wavelength is specific to the particular element, and the amount of light absorbed is directly proportional to the concentration of the particular element. So this is the basic principle behind the AAS. That is, number one is the wavelength of the particular element, and then the amount of light absorbed by the element is directly proportional to the concentration of the particular element. So these are the two critical properties involved and need to be understood in the AAS technique. And during the AAS process, elements in the test compost is broken into free atoms, that is atomization, and these atoms will absorb electromagnetic radiation at a specific wavelength. So this produces a measurable signal as absorbance. So specific wavelength, the light will be absorbed by these atoms and it will be measured as absorbance. So by looking at these signals, it is then possible to determine the parts per million or ppm levels of the elements present in the particular material. In this spectrophotometry process, atomic absorption spectrometry process, the liquid samples get evaporated and solid samples get vaporized in the process. So the basic principles behind this atomic absorption spectrophotometry is that the elements absorbing the light at a particular wavelength, and the amount of light absorbed by the elements is directly proportional to the concentration. In a simple way, we can explain. In this slide, we are seeing the atomization process happening in a atomic absorption spectroscopy schematically. Here the sample is kept and it is nebulized and forms a mist. Subsequently, dissolution will happen, and with the solid and gas aerosol state, it get volatilized. And the volatilized gaseous molecules will get dissociated to form the atoms. So the sample get nebulized to form a mist and getting dissolution with the solid gas aerosols and get volatilized in a high beam energy source and formed to a gaseous state, gaseous molecules. It will be get dissociated further to atoms. So this is the basic atomization process happens in a atomic absorption spectroscopy. So in this particular slide, we are going to see how the atomization process happens in the instrument and how the different instrument parts helping to form the atomization process. So there will be a hollow cathode lamp and there will be a source of energy which is also found in the instrument, and the sample in the solution form get nebulized and exposed to the high energy flame, and the light from the lamp will be passed through this flame. Once the sample is getting atomized after exposed to the high energy flame, the atoms will be exposed to the light source from the lamp and it is passed through the monochromator filter, and finally the light absorbed by the atoms will be detected through a detector and further it is getting recorded here. Though we understood the different parts of the atomic absorption spectrophotometer in the last two slides, in this particular slide we are listing the different parts, which includes furnace and flame, spray chamber, mirrors, cathode lamp, deuterium lamp, beam selector and photon detector. The light source employed in the atomic absorption spectrophotometry generally is hollow cathode lamp. This type of lamp contains a hollow cathode made of the element being analyzed and an anode electrode. Both these cathode and anode electrodes sealed in a hollow tube filled with inert gas. Coming to the furnace and the flame, the furnace used in the AS is made of graphite. It is in the form of a graphite tube. This generates thermal energy to break the sample's chemical bonds, producing free atoms for the analysis. There are three steps into this process, that is the atomization process include the drying, which removes the solvent from the sample, then ashing, which removes any organic inorganic material, then atomization, which generates free atoms. The flame, usually a slot type burner, is used for the analyzing fluids. It vaporizes them to create a gas. Then it comes to the spray chamber. It introduces the sample, aspirated and then applied as drops into the flame. Then mirrors and lamps. The mirrors direct the light beams from the cathode and D2 lamps, and the beam selector splits the beam into component wavelengths. Then the detector, the photon detector counts the light in photons. Photon are elementary particles or the tiniest possible particle of the light in an electromagnetic field. So the detector basically counts the photons, which is the tiniest particle of the light. The recorder, again, it is a computer system supported by a software, measure the signal transmitted from the detector. The software enables precise instrument control and acquiring, manipulating, and interpreting the data that in the process the data generated in the instrument. This is the typical image of atomic absorption spectrophotometer, which is employed in analytical laboratories. The samples are kept in this particular space and it is getting sucked through the tube and sprayed into the atomization process. Then it is getting analyzed in the instrument. The atomic absorption spectrophotometer are calibrated time to time by using copper standard solutions. The copper standard solutions at a different concentration will be prepared and these solutions will be aspirated into the instrument and the absorbance will be measured and the linearity curve will be built for the different concentration. The correlation efficient of the linearity curve should be around 0.99. It should not be less than that. Then the calibration will get passed and your instrument is working fine. In this slide, we can see different elements which can be analyzed through the atomic absorption spectrophotometry. And as per the periodic table, the group of these particular elements will have some common properties. And each and every element will have a specific wavelength to be measured. So that particular wavelength, it will be analyzed in the atomic absorption spectrophotometry. For example, aluminum 396 nanometer, manganese 403 nanometer, like that. So for the method development in atomic absorption spectrophotometer, the element particularly to be measured in a particular sample, we need to prepare the standard solutions first, the linearity standards. So the linearity standards will be prepared, whether it is a single standard or mixture of the standards. Different elements parallelly or simultaneously can also be analyzed. So the standard solutions of the element to be analyzed or elements to be analyzed will be prepared. The linearity standards will be prepared for those elements. And to prepare the sample, we need to understand the physiochemical properties of the sample matrix. So in case the sample is a tablet or sample is a solution or a suspension, the properties of this particular matrix need to be understood before preparing the sample. So here we have talked about the first standard, which is the pure standard of the elements, which is used as the reference here, and the linearity standards are prepared. Then it comes to the sample preparation will be done. And then we need to stabilize the atomization process in the instrument, and we need to set the parameters for the stabilization process in the instrument, and it will be fixed for the particular method. Then we have to analyze the standards first and create the linearity curve for the elemental standard, for which the correlation coefficient should not be less than 0.99. And then we have to analyze the sample, and the concentration of the sample should fall within the linearity range. If it is not falling within the linearity range, if it is more, then we have to dilute the sample. If it is less, then we have to concentrate the sample accordingly. So during the method development, we need to see that the stability of the sample and standards, so that you can get the accurate results. Then further accuracy and precision of the method can be analyzed or can be established to obtain a robust method. So in summary, we have the standard first of the particular element. For example, you are going to analyze the aluminium or copper, you need to have the standard, pure standard of aluminium and copper, for which you have to create the linearity curve. Then you have to analyze the sample, you need to establish a sample processing procedure, and then you have to analyze the sample, and if it is more or less within the calibration curve or the linearity standard curve, then you can directly go for the calculation process. Or if it is above or less than the calibration curve, you have to dilute or concentrate accordingly, then you can quantify through the calculations. Once the method is developed and the instrument is giving proper results for your samples, the obtained results will be used for the sample concentration measurement. So the sample concentration measurement will be carried out by linearity standard curve method. So you have already done the linearity standard curve measurements, wherein the standards will give you absorbance against different concentrations. So using that absorbance values against the different concentration, you plot the concentration in x-axis and absorbance in the y-axis, it will give you a different dots in the graph, and if you make the trend line in the dots in Excel, you will get the slope value as well as the intercept value in a straight line. That equation you will get y is equal to mx plus c. So in this, y is the sample absorbance, which you have already got it through the instrument, and m is the slope of the curve, c is the intercept of the curve, that is a constant. Then you have the x value which you need to determine through the equation. X is the concentration of the sample. So x will be calculated using sample absorbance minus intercept constant divided by the slope of the linearity curve. That is y minus c divided by m. So using these equations, the unknown concentration of the sample will be determined and the results will be displayed. Coming to the application of atomic absorption spectrophotometry, it is confined to the elemental impurity analysis. Hence, it is generally used for the quality control process of the pharmaceuticals and food, where the elemental impurities can be analyzed, whether they are within the limits or not, whether it is toxic or not, that can be determined. And toxicological analysis, it will be used for analyze the various samples. And the environmental testing, you can test water, soils, etc. for the availability of or the presence of elements in different concentrations. So these are the major applications of atomic absorption spectrophotometry in the different industries. In continuation to the applications, we are going to see some examples in this particular slide. In food and drink industry, it can measure various concentration of elements in wine and beer and also in fruit drinks. And also it can be used to find the types of contamination in the food. The atomic absorption spectroscope also used in the agriculture to analyze plants and soils for the mineral content. And metals and other substances can have a bad effect on oil and gas. Hence, in the petrochemical industry, oils and gases also will be tested by AAS to the presence of or the concentration of elements present in the oil and gases. And also, AAS used in the nuclear industry when the waste and water which is delivered from the nuclear industry will be tested for the potential hazardous elements so that they can dispatch the or they can manage the waste and water by measuring the elemental impurities present in the particular waste and waters. In continuation to the applications, for pharmaceutical companies, atomic absorption spectrometry can determine the minute quantities of the catalyst material or the metals used in the manufacture of the drugs. So when you synthesize the drugs during the manufacturing of the drugs in the API companies, the metals are used as the catalyst and the final product can be tested for the presence of these metals or elemental impurities using the AAS. And there are different raw materials requiring examination and analysis to check they have sufficient amount of certain major or toxic elements and that there are no too many impurities, some of which could be toxic. So we need to test whatever raw materials we are obtaining to manufacture certain product for the presence of various elements and to find out whether they are major elements or toxic elements and how much it is present, whether the material is toxic or not. To identify that, we need to do the AAS testing for the raw materials. So aspirants, in this module, we have seen the basics, principles and instrument parts as well as the method development and the applications of atomic absorption spectrometry briefly. And with this, we are completing the modules for the spectrophotometry analysis that includes UV visible spectrophotometry, infrared spectrophotometry, and atomic absorption spectrophotometry. In the coming modules, we are going to see the chromatography techniques. Thank you.